this panel is going to talk about relying on data science, reproducible research, and the role of policy. And I'm really delighted to introduce, as the moderator of this panel, Jess Hemerly. Jess is a senior analyst for public policy and government relations at Google, but more importantly, she's an alum of the iSchool. Over to you, Jess.
Okay, so thank you guys for sticking around. I know it's getting late on Friday afternoon. We're going to start out with some quick intros, but first my panelists wanted me to ask a few questions of the audience to get a sense of kind of where you guys sit on this issue. So how many of you use internet computing services? Okay, not all of you. Interesting. How many of you write code? Pretty good. And how many of you regularly use version control? Good coding practices. And so I think that gives you guys a good idea. Okay. So with that, I'll hand it over to the panelists. We have Victoria Stodden from Columbia University, Philip Stark, Berkeley, and Fernando Pérez, also Berkeley. So I'll let you guys kick it off.
Oh, thank you.
Sitting with
You can't sit during the presentation.
Okay, so we put together, We put together a few slides to sort of frame issues around reproducibility and how we think it interacts with big data and the types of work that we might be talking about in this room, and also, as you saw in the program, how it interacts with policy and undergirds policy decisions, as well as kind of transparency issues coming up from policy. So we put together just a little bit to kind of outline things. So defining what we think about when we talk about reproducibility and what that actually can mean in this context. Industry engagement, collaboration, and scientific research. I think it's fair to say this is happening more than we've ever seen with big data and with these types of collaborations. So what I wanted to do is reflect a little bit on what that actually might mean when we think about issues around reproducibility. And then if we have time, this notion around reproducibility and transparency is being impacted by activities in DC and in the White House. And so I wanted to talk about a couple of those because they're applying pressure on how we actually manage the data and the types of collaborations we can actually do. Okay, so I think, turn it over to Philip, I think.
Okay.
Does that make sense?
I don't know. So I can unmute myself. It's not usually my problem. My problem is usually muting myself. So I was actually really impressed to see the number of people here who write code and who use version control. It's actually not something that many people in statistics or a lot of disciplines do naturally unless they got sort of learned good hygiene as children in computer science classes or something like that. So this is the Blazing Saddles Introduction to Reproducibility, a Mongo-like reproducibility. It's good, but what is it exactly? Why is it good? Why is it hard? I mean, it is hard, and it's hard to sell. It's very hard to sell in an academic environment. I think it's a lot easier to sell in an industrial environment. And this is something where I think academia can actually benefit tremendously from importing practices and having some exchange of people, ideas, so forth and so on. In academia, non-reproducible practices are very deeply entrenched, and it's very difficult to get people to start using a different software stack, to just have different hygiene around this, just have a different workflow. So it's hard to teach an old dog new tricks, and the solution that I'm trying to take in academia is to teach the puppies, because the old dogs aren't going to do anything. So how do you train the puppies? Well, that's another kind of recursive problem, because if we don't have some old dogs who are willing to do things differently or already doing things differently, how do you teach this? So we've had a number of experiments with that. Aaron is here, Aaron Coolidge, Benoit in the audience, I think he was at one point. Victoria, all teaching classes in the statistics department, trying to get people to work more reproducibly. So why do we care about reproducibility in the first place? And I'll argue that reproducibility itself is not the goal. Reproducibility is a tool. The goal, right, is to have evidence of the correctness of what you're doing. That's one goal. How do you create affirmative evidence that you got the right answer, that your analysis is meaningful, that this is something you should really act on. Well, reproducibility is one way to accomplish that because, at least in principle, somebody could try to then reproduce it, right? It's somehow the reproduction that's the evidence. The reproducibility enables you to generate the evidence. Second, it enables the reuse, modification, extension of what you're doing. So it lets, as Victoria says, it lets you stand on the shoulders of giants or have other people stand on your shoulders or things like that.
I don't think I was the first one to say that.
Yeah, okay, well, at any rate, it's your slogan and I like it. So reproducibility, exposing your methods, transparency is somehow the methods themselves may be interesting, generalizable, so forth and so on. So that's another benefit. And then we just have this sort of gut feeling that transparency and openness are good, especially in science. We were talking about this before. I think that there's an interesting partitioning of where reproducibility and openness happens in industry, that somehow, my vision at least, is what happens internally in many industries is that what you do internally is reproducible, but then what you present to the outside world is not enough to actually be able to reproduce what you're doing because you care about the intellectual property, the trade secrets, so forth and so on. At any rate, in some contexts, it might be possible to accomplish some of these goals, like generating evidence of correctness, without having reproducibility. And I think it's a very interesting thing to think about how we might accomplish that through either scientific techniques, computer science techniques, statistical techniques, and otherwise. I'm going to move on and let Fernando, you're continue your talk? Or?
Yeah, I was going to say a couple of things and then. Okay, so I'm going to move quickly through these slides simply because I think Philip actually covered most of this, defining what we mean by reproducibility. One thing, I'll just mention like about one or two sentences. And one thing that many researchers in academia are noticing is we become increasingly computational. As Philip mentioned, we have to also adapt our practices of how we actually carry out the research and then how we actually communicate the research. So one of the things that, let's see, skip this. One of the things that people are starting to worry about is that you see these publications with computational elements in them, data-driven or even sort of software-driven, and frequently you can't actually get at the data or at the code that generated those results. So I looked at the Journal of the American Statistical Association, being a statistician, and I was concerned with two questions here. So are they actually publishing computational work, or is this all sort of something that is kind of happening in silos or whatnot? And then if they are publishing computational work, could I get the code? And so here you can see, basically at around 2009 and onwards, all the work has a computational element. I mean, it may have proofs in it, but it's got some kind of examples or some computational component. And then as of at least 2011, there was 21% of the papers that actually had some recognition that maybe I'd actually like to get my hands on the code to verify and check what's going on. And I think, judging from the number of hands from the people who do coding, I think it's probably very plausible to folks in here that if you just have the write-up in the paper, there's all sorts of information that you would need to actually implement this on a computational system. You're often missing not just sort of how the functions are written, but you're missing input parameters, you're missing all sorts of sort of details around tuning, what order did you call the functions in, and so on. So the paper itself isn't sufficient for reproducibility anymore, if it ever was. And so there's this movement around reproducibility to associate code and data with a publication so that at least you can computationally go through the steps, or at least see how the code was written and sort of go under the covers and take a look at how these results were actually generated. So I'm going to read this because I think it's very pithy. So this is a quote from my advisor, David Donahoe, paraphrasing Stanford professor John Claerbout around what he calls really reproducible research. He says the idea is an article about computational science in a scientific publication is not the scholarship itself, it's merely advertising of the scholarship. The actual scholarship is the complete set of instructions and data which generated the figures. So if you think about this and you think about the scholarly record, we have some work to do, not just in processes, as Philip was mentioning, but also in terms of what we're actually delivering when we deliver the scientific results. Okay, I'm going to go quickly just past this to give us time to talk about a few other things. Okay, so this is a book that I'm co-editing coming out in the summer. I think we're going to published it in June or July. And what it tries to do is sort of attack some of these issues around big data, around privacy issues, and how as a society we're really kind of addressing these issues. So the reason I put it up here is because there's two issues I think that are salient to this audience. So the first one is we have this tradition as academic researchers to be extremely paranoid about confidentiality issues and privacy issues, and we don't, there's good reasons for that. We don't necessarily have the best reputation historically around sort of participant protection. But now we're getting to this stage where there's so much data. It's not just that privacy inadvertently can be violated or even purposefully can be violated. There's also an awareness of a sense of agency around people's data. So people are contributing data that they feel ownership of, that perhaps describes them or their situation, and maybe they're participating in a study with full knowledge that they would like to share. And so we don't have right now mechanisms to allow that to happen. So institutional review boards are very much concerned with protecting these participants. So anything to do with privacy, confidentiality will sort of shut down data sharing. And so what I'd like to submit to the audience is, can we be innovative about how we allow people to have a sense of agency over the data and yet participate in these studies? And if they want to share their data further, can we sort of start to think about how we might accommodate that? So that's a new thing that's coming out of big data and this massive participation. The second new thing that I think is arising that we need to think about, where we've traditionally sort of locked down data, is in collaboration and industry partnerships for research. So I see over and over that people will work on very interesting data sets from an industry setting, and then it's very difficult for others to actually go and replicate or verify the work based on these data. So again, I think there's some innovation that can happen here. Are there ways we can give access to the data or share parts of the data or do things that make people more comfortable with reproducibility or more comfortable with the reliability of the findings, as Philip was mentioning, around these collaborations with industry? So I think maybe I'll come back to this. I don't know if Fernando wanted to continue, and some of the policy questions afterwards. Does that lead to?
Privacy policy.
Yeah, okay.
Oh, okay. That's great.
Should I switch into kind of my section? So in order to kind of leave us time for the conversation, I don't have any slides. I'll go very briefly over where I come into this discussion. I was trained as an academic scientist in particle physics and applied mathematics, but I've sort of led a double life over the last decade plus, which is doing academic science in a traditional setting, writing papers, writing grant proposals, et cetera, but also building open source software. I managed to get myself very involved with the building of open source tools, and I've actually learned a number of lessons from the community of open source software developers that I think are very applicable in the world of scientific research, specifically with regards to reproducibility, and we've tried to take those lessons increasingly to heart in the way we teach. The world of open source software development is a world that is not only open and collaborative, but which by definition needs to make its practices reproducible, because you can't collaborate with someone halfway around the planet on the same piece of software if they can't actually download and boot up and replicate what you were doing, if you have no way of communicating about the bugs they are seeing for you to replicate them here. So that community has built a combination, and it's very important to realize that it's a combination of both aspects of technical tooling to support the possibility of a collaborative, distributed, reproducible practice of knowledge creation, in this case of software, but it could be something else. And on the other hand, of community practices, of the practice of publicly disclosing bugs, of publicly tracking problems, of assuming that code has bugs and that what you do has errors always, and that you track those errors as part of the process, that you test and validate what you do. The incentive structure that we are faced with in science, as we were discussing yesterday at a similar panel to this one that Philip and I were in Seattle, is very much you will be measured by the height of the stack of papers that you've published. So the only thing that you're going after is making that stack higher. The moment a project is over and you manage to get it through the review process, ignore and move on to the next one and forget about it, right? And so with that metric, you optimize for very, very different things than if you're trying to optimize for being able to rely on what you've done before, being able to trust that what you've done is correct, being able to validate against the work of others that what you're doing is correct. And so from the lessons, both technical and cultural, of that community, we have been building in the open source world, and a lot of that work is happening here at Berkeley, tools for scientific computing and data science that are built with that model and with that mentality. I began a project over 10 years ago, or 12, 13 years ago, called IPython, to build interactive tools for scientific computing that began its life in Python. Today, it's a project that has a much broader reach beyond the Python language as an environment for data science where you can combine the computation and the data analytics with the narrative about the insight of what you're doing and collaborate with others. And these tools are tools that we're trying to take a very technical, obviously we're tackling a number of technical questions, but we're also trying to build a culture of collaboration and validation and reproduction of our work that kind of brings these two streams of ideas into concrete practice in the university and how we practice our research, and in the kinds of in how we educate the puppies. We're trying to housebreak the puppies with these tools so that the next generation works a little bit better in this regard. So that's kind of the context that I come to the discussion from, and I'll leave it at that.
So, a couple weeks ago we spoke sort of in planning the panel, and we had talked about kind of what sort of 4 main areas that we wanted to hit as we went through the discussion. And I think one of the things that is really important is to talk first about access. You can't reproduce someone's results if you can't gain access to that data. And so I wanted to start with maybe with you, Philip, and sort of what are some of the biggest challenges in terms of providing access and making data accessible in order to be reproducible?
So,
Are you mic'd?
I think I am.
Okay.
I mean, it's a long list. I mean, it can range from the data themselves are proprietary. The data themselves have some privacy issues associated with them, anything to do with people, for instance. It can be the size of the data. Very often the data are not where the flops are, and bringing the two together is hard. It can be that the data are controlled by someone who just doesn't respond to your emails. I mean, no.
And then Victoria, I know I actually heard you speak at the iSchool a couple years ago and sort of talking about these issues. Have we progressed since that last time?
Yeah, we really have made leaps and bounds in terms of, I think that was 2011, something like that. Yeah. So one of the things that's happened, I sort of left you hanging with that unexplained slide, is the Office of Science Technology Policy at the White House came out last year in February and in May with 2, like an executive memorandum and executive orders saying federal funding agencies that fund our scientific research are going to have to make data open, and they're going to also have to make, or come up with plans to make access to publications possible as well. And since then, even though that sort of seems maybe almost tangential, or really only if you're taking federal funds does this maybe impact you, but it's really affected the whole climate, I think, around this discussion. So you can see now what used to be sort of these discussions around how do we support computational science. It was really kind of big machinery, like do we need sort of faster processors? And now the conversation has really shifted to how do we access the data? How do we store the data? How do we make this something that people can find? How do we make it discoverable or meaningful to others so that people can reuse it? And those are not conversations that we were having in 2011, especially at the policy level. And so I think that's something that's really been this huge step forward. And I think even just having this panel here and the fact that probably we didn't need to spend 15 minutes or whatever it was introducing these ideas of reproducibility to you, it's just sort of entered our consciousness, I think, around this discussion and this debate. And I think even there was a special issue in The Economist last October on science, and they talked about access to data, a little bit access to software, and you see things like the LA Times talking about reproducibility issues, which never would have happened in 2011. It just wasn't something that we as a community were taking on. So now I think that has really changed.
And then, Fernando, as you work to housebreak the puppies, so to speak, are there particular formats that you look at or particular ways of approaching the technical issues that you think can sort of help build a better future for reproducibility and kind of lay that groundwork?
I think we have used a combination of training formats. The challenge that most of us face with this is that a lot of this right now is happening at the margins of the formal training. Philip in the statistics department has been successful in creating a couple of these courses that tackle this head on. Josh Bloom, who's in the audience and who spoke yesterday, teaches a semester-long course in Python for data science, but that is it's a graduate seminar typically attended by natural science students. It's hard. There's a much broader need across all of campus to reach everyone, and so what we have are kind of a combination of haphazard boot camps. Software carpentry is an initiative from the Mozilla Science Lab that is often taught on campus that teaches some of these basics ideas of sort of computational hygiene and data hygiene, version control, basics of programming, basics of computational literacy to scientists across the campus. Josh and I teach a slightly more advanced Python course as well. And those, we see that they work well, but we can't meet the demand. This hasn't percolated systematically into the curriculum. We're struggling with what are the right ways of doing that. And there's a very important question, which is that to really reach people in the context that they care about, we have to begin tailoring these training materials and these courses and this education to the topics and questions that they're interested in, right? And so up until now, because a lot of this is being done by few people and we have both limited time and limited intellectual depth, it tends to be a little bit one size fits all, right? We teach these things and whoever may come is welcome, but that also means that nobody finds quite what they want. You would like to be teaching the social scientists with data from a context which is different that you would like to be training the biologists with. And we still have a ways to go in beginning to tailor that better. And it's also the kinds of assumptions that you make about a given population. The feedback that you get back from these courses tends always to be that everyone feels a little bit unhappy, that it's not quite what also the background that they had, the fit isn't quite right, either too high or too low for everyone. And so we have a ways to go in being able to tailor both level-wise, assumption, background-wise, and content-wise this and fit it better into the educational curriculum of the university.
If I can just add to, so I've been actually using Fernando's software in a course that I've been teaching here this semester, and speaking to what you said about sort of formats and some of the design issues, one of the reasons we made the choice to do this is because it doesn't constrain you to work in a particular environment that's installed by this particular software, and then you have to work in a particular way. So I think that type of flexibility, I don't want to put words in your mouth, but I'm imagining that was built in from the beginning to allow this kind of flexibility in adapting to the different environments. And to me, that's a more successful approach than, install this and then work within this world, and then everything will be reproducible.
No, that was definitely something that we've worked hard to try to reach.
I mean, I would also think that you chose Python for a very good reason.
Yeah, so the choice of language initially was not an accident. Specifically in IPython, I fell in love with the language, and I had my computational problem was simulations in particle physics and quantum chromodynamics specifically. And one day I looked at my desk and I had this hodgepodge of books. And I saw I have a book on mathematics, I have a book on IDL, I have a Unix book about awk, sed, and bash, I have a book about Perl, I have a C book, I have a C++ book. And I realized I'm spending all of my time context switch, and that was because I had code in each of those things in my analysis and computation pipeline, and I was just spending an insane amount of time context switching in my head between these things and forgetting the details of the syntax of each of those. And so I discovered the Python language in 2001, and I realized I can actually collapse a lot of that stack, maybe not all of it, but replace a lot of that with an open source language, which means I can share my work with others without licensing worries. That actually has a combination of being high level and being technical enough.
So there is a language.
So that it is a language, not like IDL, for example. And that really allowed me, I sort of fell in love with that. Now that meant that I got sucked into building the scientific Python ecosystem, because at the time it was very much nascent. But it's been a productive gamble overall. What's happened though in the intervening 13 years is that now the IPython project has taken kind of a broader view of what does it mean to do computing. And actually the IPython environment now supports as first-class citizens, not just Python, but R and Julia and MATLAB and basically just about any language that you can use. So that, going back to what Victoria was saying, if your environment is that you're doing heavy-duty R data analysis, that can be done natively as a first-class citizen in the Python environment, not just Python. Though it remains our internal implementation language for the end users, the goal is to enable people to share computational work and insight extracted from data in the best possible way, not to force everyone to use Python.
I'm wondering whether it's worth talking just in really broad terms about the architecture, about what it accomplishes. How many people have used IPython?
Or IPython.
Okay, almost everybody. All right. Okay, so you have the idea that you're somehow packaging your computations and documentation and graphics and everything else into a nice little thing that you can share with other people. You can reproduce what you did. You can roll back the clock. All of these things that really...
And as a convenient environment just to track what you're doing as you go, like the notebook idea, like sort of mimicking the lab notebook, I think is where we got this idea. So.
Yes, and these kinds of environments had been built back in the 90s by systems like Mathematica that I used heavily as a graduate student. So these ideas of combining text and code and results were there, but what we tried to do...
Don't invite litigation, careful.
was, this is science and we build upon the shoulders of giants. We took an idea that was implemented in the 90s and we sort of reimagined it in the context of the web. And how do you imagine that idea, but you imagine it as a cross-language, internet-enabled environment where the computation is on one end and what comes back are web-native objects. So the reason why we can display basically anything that comes back in the browser is because we adopted web protocols, JSON data formats, HTTP internally for the transport of a lot of the data, so that it's sort of imagining how would we build a computational lab notebook environment today in the age of the internet in 2010, 2012, which is when we really started doing this design.
There's another thing I can add too. So I think this notion of making your work open and available to others to support reproducibility has sort of obvious implications for science, but in the classroom too. So, if you have students doing a project and coming up with analyses and they have to sort of put this all together in a report and hand it in, it's much easier for me as an instructor to kind of see what they've done. And, it's not just kind of this black box where I trust them or I have some scripts that I have to kind of get going. So it's actually just from the teaching context itself, within just that environment of the classroom, been extraordinarily useful too.
So the executable document, and then going beyond that, working in some kind of revision control system as well makes it much easier to have a look into what the students are actually doing and when.
Great.
I mean, I've been given permission to go slightly longer than 3:30, so I just want to ask one more question of you guys, and then we'll open it up to the audience. And this is sort of, I want to tie it back to kind of the broader theme of this conference in general, which I hate the term big data. But one of the biggest problems that we're seeing emerge in sort of the big data world is spurious correlation.
Is the politically correct term differently sized data?
different. Size doesn't matter. But one of the biggest concerns is that people are going to confuse correlation and causation and things like that. And so having talked to you, since I first talked to you, I've been thinking about this quite a bit, and I really feel like reproducibility is one of the keys in kind of taming sort of the world of insight that's drawn from big data, and I'm wondering if you have any thoughts on that and sort of the role of reproducibility.
Can I jump in on that one? So you switched so I think what happened there is you switched the meaning of the word reproducibility just a little bit.
Yeah.
No, this is really important to clarify. So there's reproducibility, so this is not this is just how the term gets used. So reproducibility in the sense of, can I actually replicate the computational steps you carried out to get those results? So that's sort of what we've been talking about for the last couple of minutes. And then I think where you're going with that question, and correct me if I'm wrong, is in the sense of sort of, can I verify results and understand which results are reliable and stand the test of time? And particularly when you have issues with so much data that when you run sort of traditional, if you sort of blindly run traditional statistical tests and come up with a p-value, you end up with a lot of significance, and a lot of it seems very spurious. So I think there's sort of two ways of thinking about reproducibility. Can I sort of independently replicate and come up with the same results? I think that's maybe...
I actually meant the former. I did mean the computational steps.
You can go through computational steps on terrible work, and it's reproducible.
You can also have, I think, two different people who run through the steps and see the data differently, and I think that's sort of what I'm getting at.
That's the independent replication, right.
But with the same computational steps. I mean, as a student who's looked at Python and looked at other people's code, you can kind of run it the same way, but you're seeing it differently.
No, and I do agree. Sorry, Philip, go ahead.
No, I'm not sure I'm quite following. So Are you saying that the interpretation of what you're looking at is different, or are you saying that you're generally applying the same algorithms but making slightly different choices that are resulting in different output? That. Okay.
And I also think, if I'm understanding correctly, that I would agree in the sense that even though it's not a panacea, being able to reproduce someone else's work verbatim isn't going to solve the problem of them having misinterpreted spurious correlations. But at least if I can replicate it, now I can go back and have a more critical eye. Absolutely. If all I have is an answer and I don't have the code and data, well, I'm stuck, and I may believe that they're wrong. I may question why they came up with an answer, but I have, other than flailing around and waving my arms, it's very hard to critique it. Whereas if I can go in and say, wait a minute, look, and in this part of the code, you actually ran a massive amount of multiple comparisons and you're not doing any kind of corrections for that. It's much easier to have a more informed dialogue and a more critical dialogue if I can get into their computation than if I can't. I think that's...
Let me see if I can tell a longer story about what I think you asked, and then you can correct me. So, I mean, the analogy on some level is, here I am, can I actually redo what I did and get the same answer? So I might not even understand what I did, I might not have been the appropriate thing to do, but this is sort of like a scientist at a bench in the laboratory, go back to the bench the next day and have the same result. And then you're sort of saying, well, what if somebody else in a different laboratory kind of starts from the same compounds, so forth and so on, but follows slightly different lab procedure, are they going to get essentially the same result? And then there's something else, which, well, does it generalize beyond that to the world at large? And it's very difficult to know what aspects of the analysis are somehow points of leverage, where there's vulnerability, where very, very slight changes to exactly what you did are going to result in completely different answers, separate from what would happen if you actually started with different data, if you run a different experiment. So we don't have terms to describe all these things, but what I understood you, I think, to be saying is like the second one. So I might be able to push the button and get the same answer, but if you do what I did the way I described it, but not having described it in excruciating detail, but try to re-implement it, are you going to get the same answer? Is that?
I think Fernando really nailed what I was asking, actually, okay. But you've all given really useful answers to my apparently confusing question.
It's a confusing topic.
Yeah. So yeah, I think it's more as a means to an end and sort of helping to educate and understand.
And there's a great example, I think, of what you were talking about, which is the recent scandal of Reinhardt and Rogoff, right? Where only the moment that people were, for those of you who may not be familiar with it, it was a publication about how debt levels beyond about 90% debt as a ratio of GDP in countries would send countries into a spiral of growth crash, which was used to justify a lot of the austerity policies in Europe. And then when people actually tried to replicate the experiment, they found out that there were errors in the spreadsheets that they were using. The data had been miscounted and misaveraged. And so this is one of those cases where simply being able to go into it, you may find, this wasn't a case of correlation, but a similarly statistically invalid answer was being pulled out of the data. Just somebody being able to go into the data and replicate the analysis would be sufficient to say, well, wait a minute, there's a problem in here in how you treated your data.
Can I ask the audience, how many of you use spreadsheets by choice?
Yeah, slowly and hesitantly.
So questions from the audience?
So earlier, Victoria, you showed a slide of the statistics now on publications that are sharing their data and their code. Maybe each of you could take a stab at when you think maybe 51% of computational publications will include that kind of information.
Okay.
We'll all be dead.
No, we're not, unless something happens. Okay, so I'll go on record saying 10 years. And I think 20 years we're doing 100%.
I think it's going to depend enormously on the discipline. And I think one of the things that working in a reproducible manner makes it much easier to do is to collaborate with others. So I think that it's likely to happen with big science faster than small science, because the need to be able to collaborate with people is going to necessitate it. I don't know what that means. Maybe that means in the omics kinds of things, it's going to happen sooner than it will in others. On the other hand, in some kinds of really big science, like CERN, Large Hadron Collider, can be very difficult to look into what they're doing and have them be transparent for a long, long time. So I guess some kinds of big science and others not.
What he said. that was going to be my answer.
Yeah.
So you talked about sort of this great bottom-up sort of groundswell around reproducibility, and the three of you are kind of leading the charge on that. And now there's also this sort of top-down thing from the highest levels of government. I guess I worry a bit about that from the top down being an unfunded mandate. And for those that don't have the opportunity to learn sort of best practices, I think when the NSP or NSF starts saying you've got to do this, as a CYA thing, essentially, a lot of people won't have received that training, and effectively that just means more money will be required from them to do it. All right, is this something, I guess, Victoria, you thought a lot about this, that you're particularly worried about? And how do we deal with it?
So then there's another angle to what you're saying too. So notions of reproducibility, data sharing, code sharing, as you probably, just from our discussion, we think there's, I don't want to speak for them, but there's skill involved in doing this. You can't just sort of take things that maybe you did in sort of the olden days and kind of throw this out there. And so there could be differential impacts on different types of researchers. So researchers that are more computationally proficient may find this easier versus other ones, and that's no reflection on their qualities as scientists necessarily. So there's many issues actually to be sensitive to here. I also worry about sort of pressure from the top for another reason, which is Philip and Fernando have talked about sort of the sort of granularity of the problems, and different areas will take sort of different approaches and focus on different things by necessity, just by the nature of the questions that they ask in their field. And so you sort of have these top-down approaches which are necessarily not going to fit. The only reason, there's only one reason that I think there's something useful there around these top-down approaches. It's because we're so peer-oriented as the academic community that we end up in this collective action problem. And it's very difficult for someone to take the extra time to do work that's reproducible, share data, share code, not do what Fernando was describing, just sort of build your stack of papers and so on, because their career suffers. And it's changing, but it still suffers. And so something that can kind of move us all together to a new place, I think, is really something that's actually useful to sort of get us out of that local maximum.
I'd like to say three. I know we're running over time, but one is, I think the mandates that are coming down are not very
useful.
Well, they're not very broad. They're not. I mean, they're not asking for much, right? Yet, it would be nice if they asked for more. So I think complying with the current mandates is not that big a deal. And I think that the cost that you're talking about is largely a cost of education, which is microscopic compared to the cost of the data acquisition and everything else that's happened. And so I think it's kind of in the noise. It's much more the human friction around, how hard is it to learn something new, as opposed to what does it cost to teach somebody. And then the other thing that we haven't talked about at all is, at least within the academy, we really do, I think, need to change the incentive structure. We really have abandoned science. We've gone from the scientific method of show me to the scientific to saying just trust me, right? And if you're not working in a way that's reproducible and exposes what's going on, why should I believe your result? And the whole academic promotion procedure that says, you sort of think about it. Oh, how nice that you advertised your work in Science and Nature and whatever, but where's the work? Show me the work. I actually want to know, show me that I can rely on it, so forth and so on. So I think that this just trust me thing is going to break at some point, going to break badly. And that's maybe when things will start to shift.
Yeah, so I think you kind of just covered what I was going to talk about. But going back to Reinhardt and Rodolphe, and is there some sort of kind of aversion to sharing that because exactly that huge embarrassment spun as kind of this major upsets, kind of defensive press on their side that our results still stand? Is this something that you think people are actively trying to avoid because of embarrassment like that? And do you think there's an incentive out there at the moment for that?
I think some people are afraid of public humiliation. No, everybody's afraid of public humiliation. Some people change what they do because of their fear of public humiliation. But I mean, if you really are a scientist and you want to know what the truth is, you want to do work. You want your work to be right. So exposing what you're doing. I mean, I love it when people find problems with what I'm doing because I want it to be right. And I'm not. So I think there's a huge variance in people's motivations for working one way rather than another. And the open source community is what you do. You show your code. I mean, code reviews for academics, it's excruciating, right? But absolutely necessary.
But I also think the Reinhardt and Rogoff example is exactly the perfect illustration of what's wrong with the system. The embarrassment doesn't come from the fact that they made a mistake. The embarrassment comes from the fact that they claimed a result and hyped it for years, and then a mistake was found. If the process had been a more open one from early on, that mistake would have been found when it was an inconsequential mistake early on, because we all make mistakes. Making mistakes, errors are part of the natural process of science, and that's why in the open source the process of development, you're not trying to review something that has been hidden away for 10 years and then all of a sudden you land it and oh my God, how could you have done that? The review process, the detection of bugs, the testing of the machinery is an ongoing continuous process. So no one feels any major embarrassment about any one problem because it is the nature of the process, right? Which is very, very different from saying, I'm going to make this past the reviewers, right? There's another classic case, the Nevin, the Potty and Nevin case in Nature Medicine in 2006. Too long to describe here in short, but basically it's an issue with reproducibility of results in cancer therapies that led to resignations and lawsuits and people ending up dying because the data had been kept hidden and stuff was published in Nature Medicine. It made it past the peer reviewer, so this must be true. Patents were filed, patients were put in clinical trials, and it was only years later when Keith Baggerly at MD Anderson Cancer Center in Texas finally did the forensics, was able to do the forensics on that after years of work, that they discovered this was all wrong. But none of that would have been an issue if the process itself was different, right?
I'm going to say the same thing kind of again, which is if the mode is trust me, and then you discover that I made a mistake, you've just found that I'm untrustworthy. If you're saying show me, and I show you my argument, you say, oh, there's an error on line 2.
That's okay.
That's okay. Everybody makes, I mean, it's a very different thing. So in one case, you've been revealed as untrustworthy. The other case, you're just human. Right?
Okay, that's all the time we have. Thank you, guys.
Thanks a lot.